my name's Colin Power from Into Infinity, and today we're going to be solving the world's most challenging problem of the last century, Continuum Hypothesis, using just a piece of paper and a pen.
Holy fuck!
Before we do, let's have a little think about this nature of infinity. It started to become quite a topic at the end of the 1900s when a guy called George Cantor described something called an infinite set and started to differentiate between different types of infinity. So here we have a line and it's divided into three. Yeah? And what George Cantor did, he said, what happens if we remove that line? And you'd be left with just two. Yeah? So 1/3 would be missing. Yeah? And then if you can also divide that and take out the middle third of these parts and another third missing there, third missing from there. And each time we move through, we're removing a third section from the middle of each line. And so you can continue moving a third into infinity. Yeah. So the gap here, there's an infinite number of those gaps that you can create. Yeah. Those gaps there. There are also an infinite number of these things here. But if you think about it, because there's two of those, this is a larger type of infinity than this infinity here. This infinity has 1, 2 for every one that's missing there. So that's 2 for every one there. So that shows you that there are different types of infinity. It was the birth of something called fractal geometry. This caused a little bit of a stir in the mathematical community, you could say, but it did lead to something which is the foundations of modern mathematics called set theory. And so the concept is that we can have different types of set. So for example, let's take all of the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on into infinity. We could say that is a certain set of number. But the problem is as we go through these numbers, there's a lot more numbers in between here. Look, that would be 0.5, for example, yeah? With 2.5, yeah, wouldn't it there? And actually there's an infinite number of these tiny little divisions in between each number space. And that creates a sort of bit of a conundrum, really, because in this sense, we could say that this is one set of numbers, and that set of numbers is an infinite set, but it's smaller than this, which they call the infinite set of real numbers and everything else like that. Yeah, Aleph1 is all of these whole numbers, and Aleph0 is including all of that set, including all of those small numbers. Yeah. To solve the continuum hypothesis, Cantor suggested that there was no infinite set that existed between those two. If you imagine, it's like you have to think of things in terms of density. What's the density of the numbers, And so with those unit spacings of those numbers, it's just going up 1 plus 1 plus 1 plus 1 plus 1. Whereas with the infinite decimals, it's very difficult to determine how much it's progressing. So it's an infinity even between the numbers 0, 1, for example. There's an infinite number of decimals, yeah? They can start with a 0 point, And because of that nature, it creates a paradox in mathematics, you can imagine. Aleph1 would be the whole numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 into infinity, whereas Aleph0 would include all of the decimal fractions as well. Is there an infinity between Aleph1 and Aleph0? And we're going to prove that there is actually an infinity between Aleph1 and Aleph0. So to start with, we've got a column over here, we write the number 1 in there, yeah? So that's step 1. And over here, what we're going to do is we're going to write 1 over 1. It's a fraction, yeah? 1 over 1 equals 1. So let's go to the second step, yeah? And here we're going to go 1 over 2, and then 2 over 2 equals 1.5. And as we go to number 3, we're going to go 1 over 3, 2 over 3, and 3 over 3. Like that, and that equals 2. And I'll go to the you can see what's happening here is that every step this takes, a one step, it goes 1 and jumps down there. When this jumps down, it jumps down just a half. And this jumps down to 1, this jumps another half, this jumps to 1, this jumps another half. And so this is progressing at 1/2, of this, which is progressing at 1, yeah, and it will continue like that on into infinity. And so each one of these lines connects along like that, and really what you get is, if you think about it, you get a square like that with a diagonal going straight the way through it, yeah, and we call that the square root of 2, yeah, if we call that a unit of 1, yeah. So that's the square root of 2 going across that middle line there, yeah. Now, if we take Aleph 0.5, because it's only progressing half.
Hell no, man. What the fuck, man? Get your ass on, boy. You get your goddamn ugly ass.
This is shrinking, yeah, in size. It's only stepping up in half. What you would get is, if we turn it into our square again, this would be the halfway mark, and this would go like that, and that would be the geometry of that. And then this here would become the square root of 1.25. But you can see here that there's a geometric nature.
Now hold on just a second. Pause the movie. Hit pause.
Oh my God.
To this type of infinity. That this infinity is denser because it's compressed. And that means we can compress things to the halfway mark, the 0.5 mark. And that's why we call it Aleph 0.5. So that's resolved the continuum hypothesis. The question was, is there an infinity that is, falls in that straight line between, the Aleph 0, the infinity of all numbers, to Aleph 1, which is the infinity of the whole number set, and there is an infinity between the two, and it's the fractional numbers between 0 and 1. And that proves that George Cantor's conjecture that there isn't an infinity between these two wrong. And there is actually one, and it's called Aleph 0.5. And now Aleph 0.5 has many implications for a lot of other things in mathematics that we're going to look into next, yeah? But before we do, we're going to also maybe give a bit more of a satisfying solution to what this kind of means for numbers and infinite set theory. So coming up next, yeah, will be a solution to the... To subscribe below, and if you want to follow along with us, and if you like what you see, do subscribe to our Patreon, and where you can get access to webinars and talk to us more about all this sort of stuff directly. Thank you very much. My name's been Colin Power. You've been awesome, and this is Into Infinity, taking you beyond the matrix.